So today let's take a look at some interesting LEDs. Those are interesting because they are designed to run directly on mains voltage with no power supply, no driver. They are chip-on-board or cob LEDs which contain the LED chips on some board, and they also contain some integrated driver in it. I have already made a video about one of those, and in this video I was explaining how does it work and what's happening in the circuitry, and I did some oscilloscope measurements and I drew the schematic of it, but I didn't really test it properly. I just ran it for a few seconds, did some measurements, and I didn't even put it on a heatsink properly, and I didn't try to run it for a longer time. And there is a link to the video in the description. But now let's try to build some light using those LEDs. Let's try to put it on a heatsink, and also let's try to measure the power of them, and let's see if they can last in a long run. Those LEDs are quite simple. The mains comes in, there is a bridge rectifier, and there is no smoothing capacitor in it. And the rectified mains goes through the LEDs and through some current regulating chips, and those chips are just linear regulators, not switching, so they dissipate power. And they have some current setting resistor or current sensing resistor to set the current, and those are usually 6.2 or 7.5 ohms in those LEDs, and some tiny capacitor for stability. It's not a smoothing capacitor, and it can have one chip or more chips in parallel in it. And the chips have 8 pins, but most of them are just connected with each other, so in fact it has just 3 terminals. The positive, the negative, and the current setting resistor. And it basically regulates the current such a way that the voltage drop of the resistor is some certain voltage, let's say 1 volt. If the voltage is lower, it will increase the current, and if the voltage is higher, it will reduce the current to keep the current constant. Of course, there is way more chips than I have drawn. They are all in series. And here you can see one of those LEDs, and according to the color of the phosphor, it's probably a warm white LED. And here you can see the bridge rectifier and some 0 ohm resistor, which is maybe a fuse, but maybe just a jumper. Here's the capacitor, just a tiny capacitor for stability. It's not a smoothing capacitor, and here's just one chip. This one is the least powerful one. It has one chip and the current setting resistor, 6.2 ohms, 6R20. And so the least powerful one, which says 20 watts, has just one chip. And this one has 2 chips, and it says 30 watts. And it's probably cool white, according to the color of the phosphor. And the phosphor is more transparent than the warm white one. And you can see the chips, quite a lot of chips, all in series. And again, a bridge rectifier, a 0 ohm link, a capacitor here, and 2 chips with current setting resistors, 6R20, 6.2 ohms as well, and those chips are in parallel. And the last one says 50 watts, and it has 5 chips, 4 chips here and 1 chip here, and each of them has positions for 5 chips, but some of them are not used. And this one has different resistors, and now I noticed the resistors are not the same. This is 7.5 ohms, 8.2 ohms, 7.5 ohms, 8.2 ohms, and 7.5 ohms. But this is probably just to fine-tune the current. And the chips are probably all the same. But it seems like they have no marking. And there is some resin on it, but even after removing the resin from one of those, I can't see any marking at all. So those ones have chips with no marking, but the older one, which I already tested, has a chip with a marking, and the new ones have a transparent resin on the chips, and this one used to have some white resin on the chips and on the resistors, which I already removed. This all was in resin, and as you can see in the older one, the chip has a marking. BP513TUH. But the new ones have no marking on the chips, but it seems like it could be the same chips. And this older one is more or less the same. It even has the same resistor values as some of those resistors here. And the older one actually seems to have more chips in it, but it doesn't have. There are some empty positions on the board. Only every other position for the chip actually has a chip on it. So the actual number of chips is the same. Or actually the old one has 74 chips and the new one has 72 chips, but it's almost the same. And those LEDs also come in a 110 volt version, and here you can see some keywords in the listing. They are called LED cob lamp or floodlight with integrated smart driver or chip or IC. And here you can see the available powers of the LED and the prices, and those prices are including shipping, so they are super cheap. And the LED basically runs on a mains voltage with no smoothing. This is the mains sine wave, and here it's after the rectification. And the LEDs only light up when the rectified mains voltage is higher than the voltage drop of the LEDs, all in series. And in the older LEDs there is 74 chips times 3 volts per chip gives about 222 volts. So the LEDs only light up here from this point to this point. So this is where the LEDs are lit. And in the other half cycle the same happens. So the LEDs light up here. And the voltage dropped on the chip is this. And it changes as the voltage goes up and down during the sine wave. So this is dropped on the chip, and the area, the red area, is the average power dissipation of the chip. So the green area is the actual power input of the LED chips, and the red area is the power dissipation of the chip. So you can see most of the power goes into the LEDs, but there are also some losses. And you can also see that the LEDs light up for just about half of the time. They are lit from here to here, and they are off from here to here. So it's roughly 50% on time. So it flickers horribly. You can't see it when you take a look at it, but when you, for example, move something quickly, or if you move your eyeballs quickly, you can see it. And also because the LEDs are running only half of the time, the power of them has to be about double. So in a 20 watt LED, the peak power is about 40 watts, and in the 50 watt LED, the peak power is about 100 watts. So the chips are actually set to run the LEDs at about double the power because they have about 50% duty cycle. So if the mains voltage changes a bit, the power of the LEDs also changes. The average power of the LEDs changes. The peak power is regulated, but if you increase the voltage of mains, for example, then the voltage is higher than the voltage drop of the LEDs for a bit longer, so the LEDs run at a bit higher duty cycle. And if the mains voltage is lower, then the voltage stays above the voltage drop of the LEDs a bit shorter, so the duty cycle is lower. So the mains voltage doesn't change the peak power of the LEDs, but it changes the duty cycle of the LEDs, and thus it changes the average power. So the power of it depends on the mains voltage, but not as steeply as if there was a resistor in series. So the chips are better for the regulation than just a series resistor, but still they are dissipating power because this is not a buck regulator, a switching regulator with an inductor. It's just a linear regulator which dissipates the power. It basically dissipates the power, which is the voltage drop times the current. If it was running on a smooth DC voltage, those chips would be just as inefficient as a resistor, but because it uses a rectified sine wave with no smoothing, the chips are a bit more efficient than resistors. Which may seem strange, but it's really this way because a resistor would pass most of the current when there is the highest voltage drop, but the chip still passes the same current from here all the way to here. So even if the voltage on the chip is very, very low, it still passes the full current, and in those 2 points it runs with almost 100% efficiency. But a resistor would pass most of the current here, and in those points it would pass virtually no current. With a resistor, most of the current is concentrated here, where it drops most of the voltage, but the chip actually passes the same current from here to here, so in average, the chip is more efficient than a resistor. So the efficiency of it can be, I guess, about 80, maybe 85%. When the mains voltage is higher, the efficiency is lower, of course, because the chip in average drops more voltage. Now let's try to test those LEDs. Let's try to put them on a heatsink and power them. So let's use a vintage heatsink I've got from some power amplifier, audio amplifier, probably from 80s. And it contains some transistors. One is a Tesla transistor, which is probably original to the device, and the other one is some Motorola transistor from 93, and this one is not original. I have put it on the heatsink for some experiments, and I actually took a peek in the transistor. I opened it here to see the dye in it. You can actually open those transistors and take a peek in it. There is no resin in it, and they still work. Opening it doesn't damage the chip. So now let's remove the transistors and drill some holes for the LEDs. So the transistors are removed, but of course I keep them because those transistors are quite good. For example, for power amplifiers like audio amplifiers, and also for power supplies for linear regulators. This is a Tesla transistor made in probably 80s. So let's put the LEDs on it without much measurements. Let's use my saw to measure roughly the center of it, and the LED goes here, and I will probably arrange it such a way that I can put 2 LEDs on it, like this. So let's put the LED roughly here. Let's mark the holes. And theoretically I could even reuse the holes, like this, and later put 4 LEDs on it. So let's drill some holes in the heatsink. And what's the size of the mounting holes in the LEDs? A screw number 4 doesn't fit, so let's try screw number 3. It fits. So let's drill some holes using some drill bits. This one is for walls. It's not suitable, and this one is for steel, so it should be okay for aluminium. I've got different sizes, and for screw number 3 I should probably use a drill bit which is 2 millimeters, because this one 2.5 millimeters is too thick. And if it's too small I will use 2.5 millimeters drill, but I think the hole will be big enough with 2 millimeter drill, especially because it kind of wiggles when you drill it. And then of course I will make a thread in the hole using those tools. It's aluminum, so it should be easy. And there is number 4, number 3. So this one is the one. And the set contains 3 different ones. And this one has the steepest tip, and this one the least steep tip. I'm not sure which one to use, but I will probably try this one, because the hole goes all the way through. Some other drill bits and tools here, and I will probably use the 2 millimeter drill bit from this set. Can I do it using my hand drill? Even though, of course, this one is better for woodworking, not for metalworking. But anyway, does it work? Yeah, it works. But of course this is going to be way faster. That's it. Now let's clean it a little bit using my scissors, of course. It's definitely not the right tool, but scissors can do everything, of course. Now let's try to cut the thread, and this tool is probably not supposed to go into a drill, but anyway, let's try it. Let's switch it to slow. And let's try to cut the thread, of course at an angle. Do I cut a thread or do I drill it? I'm not sure. I probably failed now. Okay, so it seems like the hole is too small. Let's use a 2.5mm drill. A 2.5mm drill bit. And let's try to cut the thread again. Now it seems to work way better. Another hole. Let's reverse it. Nice. Another hole. Let's reverse it. And that's it. Let's clean it again. And of course, if there is some professional machinist watching me, he's probably getting a heart attack, but anyway, I even managed to make the holes with enough accuracy so it fits. Now let's try the most powerful one, 50 watts. Let's put some heatsink compound on it, quite a lot of course, because there is never enough of heatsink compound. And that's it. So let's put some screws in it with washers and springy washers, and of course those are slotted screws because I like those vintage ones for a flathead screwdriver. So the LED is mounted on the heatsink using my vintage screws and a lot of heatsink compound. But now I realized that I should have probably soldered the wires onto it before putting it on a heatsink. The heatsink takes the heat away, so now it will be probably very hard to solder on it. But let's try to solder it anyway, using some solder, some rosin and my soldering gun. 100 watts, it should be enough for this. So now let's thin my cable and solder it to the LED to be able to test it. I put some rosin on the wire and some solder or tin and solder it to the LED. And this old cable is a bit oxidized. But anyway, with a lot of rosin, I can still solder on it. And that's it. So now it's soldered and the question is what happens when I plug it in. And it's the most powerful one, 50 watts, with 5 chips on it in parallel. And of course here's the cat, which comes in the most dangerous moment, of course. So now the cat is gone and let's test it. Wow, it works! It's a cool white LED, quite bright, but of course in camera it flickers. Let's try to measure the power. And the power is 56 watts. Bloody hell, that's powerful. Now the question is, how long does it last? I can actually feel the heat radiating from it. Not the actual heat, but the light is so strong that it has a heating effect on my hand. Now the question also is how much the heatsink pad of the LED is isolated from mains. The isolation is probably almost non-existent, but I'm not touching anything grounded, so I can touch the heatsink now, which is not yet hot, it's almost cool. 58 watts, and it's super bright. But of course it flickers in camera because it has no smoothing. It's just a horrible flicker. But I can't see it when I take a look at it. But when I, for example, move my finger quickly, I can actually see the pattern on the finger. Now let's try to take a long shutter picture of a screwdriver moving in front of it. And this picture basically is what I can see briefly with my naked eyes when I move the screwdriver in front of it quickly. For comparison, let's try to do this experiment with this torch. If the LED runs on a smooth DC current, you can see no strips. Now let's try to measure the temperature of the heatsink using my makeshift thermometer. It's a makeshift solution which became permanent, of course. Here's the probe on the heatsink, and the heatsink is actually getting quite hot. After about 10 or 15 minutes, it's already a bit too hot to touch. So the idea of putting more LEDs on it is probably not such a good idea. Now let's try to run it a bit longer. The temperature goes up. After half an hour, it's 71 degrees Celsius. Now it's running for 2 hours and the temperature settles at 83 degrees Celsius, which is about 57 degrees above ambient. So as you could see, the heatsink was getting quite hot, but still kind of acceptable for the LED. And as you can see, dissipating 50 watts of power, it's not easy even with this huge heatsink. Of course, the heatsink would be more efficient if it was black or if the fins were vertical. Dissipating so much power with no fan isn't easy at all. And the LED is quite nice. It ran for 2 hours with no failure, and for such a cheap LED, it's actually not bad. It's quite bright and the efficiency probably isn't the best you can get with an LED, but still quite nice. The biggest disadvantage is the flicker. It's not visible normally, but if you move something quickly or if you move your eyeballs quickly, you can kind of see it, and the flicker sometimes interferes with the camera, with the rolling shutter or the frame rate of it. The camera can especially see the flicker when the light is very bright, for example when you point the LED directly at the camera. Otherwise, sometimes it's not visible in the camera. Now let's try to measure the flicker using my oscilloscope connected to this crappy solar cell, which is from the crappy dodgy Chinese solar camping light. I will load it with a resistor and measure the voltage on it using my oscilloscope. So here's the solar panel illuminated by the LED, loaded with this resistor and connected to my oscilloscope. And this is more or less what I expected. Even though it's a little bit less vertical than I expected here. The top of the pulses goes slightly downhill, and this is probably the temperature drift of the chip. As the chip gets hotter, it slightly reduces the current, and let's try to zoom it a little bit. And this is really not vertical. It's probably because of the internal resistance of the LEDs, but it's better because when the LEDs don't turn on and off suddenly, it produces less interference. It's really better if the current goes up and down gradually. And if I zoom this part of it, it seems kind of dotted. So it looks like some oscillations in the chip maybe. Can you see it? The falling edge is dotted, the rising edge is not as dotted. Now let's try the 20 watt LED, which is probably warm white. Is it going to blow up when I turn it on? No, it works. It flickers and it's a nice warm white light. And the power of it is just 15 watts. That's not much. So this one is definitely not going to overheat. And now let's try this one, 30 watts. And the 30 watt LED is actually 29 point something. It's quite close to 30. That's nice. And so those LEDs are quite nice. The only disadvantage is the flicker and some losses in the chips, but they probably couldn't fit a switching buck regulator in it because the inductor would be too high. It would be sticking from the board and they couldn't probably then fit it in some reflector because those LEDs usually go under some reflector which is usually quite flat. And they also couldn't fit any capacitor in it for smoothing because it would have to have enough capacity, so it would have to be an electrolytic capacitor. But electrolytic capacitors are big and they also don't like heat, so it couldn't be directly on the board. And here's my cat, of course, in the view again. And she likes my screws. And so those LEDs work nicely. I didn't even have to use my fire extinguisher today. But of course it's probably not a good idea to run both LEDs on one heatsink, because even with one LED it was already quite hot. But could I somehow reduce the power of the LEDs, because running more LEDs at a lower power would be probably more reliable and also more efficient than running just a single LED at a full power, because LEDs generally run more efficiently at a lower current. I can try to remove some of those chips or change the values of the resistors in the LEDs. So now I've desoldered 2 of the chips, so the power should be about 60% now, with just 3 chips remaining. So it should be now about 34 or 35 watts. Just 13. I probably broke some connections to the other chips. I broke some track on the board when I was desoldering the chips, so I put a piece of wire here to fix it. So it's now fixed and the power is 36 watts. Now let's put some terminal block on it, because like this I can easily pull the contacts of the LED off. So let's put a terminal block here and connect both LEDs. So let's cut the terminal block using scissors, of course. That's it. And let's give it a proper cable with a ground for the heatsink. Let's remove the isolation using scissors. And that's it. It has a proper cable, a strain relief, it's grounded here onto the heatsink, and both LEDs are connected. Now let's test it. Does it blow up? No. Both LEDs run and the power is about 66 watts. Nice. And here you can see the chips of the LEDs at a very low current. And what's going to be the temperature of the heatsink? When I put it vertical, it should be more efficient. Now let's measure the temperature after it settles. It runs at 66 watts. And now the temperature settles at 66 degrees Celsius, which is significantly less than before. Despite there is more power to dissipate now, and this is because the heatsink is now in a vertical position. So as you can see, the heatsink works way more efficiently with the fins vertically, not horizontally. And here's my illuminated cat. And after 2 hours the temperature seems fine. Nice. And my cat calculated the thermal resistance of the heatsink for me. This is in the horizontal position and in the vertical position. And the thermal resistance of it is way lower with the fins vertical. Of course, some of the input power comes out as light, so there is less power dissipation than this, but the ratio between those 2 numbers is still the same. It doesn't change the ratio between the vertical and horizontal efficiency. The vertical position of the fins reduces the thermal resistance by about 40%. So this is my LED light, even though it's still quite dodgy because it has no fuse and no cover on it, and it's live at mains voltage in those connections. So this is Diagon Wild, and see you in my next videos, and thanks to all of my patrons on Patreon. I really appreciate your support. And I also think about how to get rid of the flicker of those LEDs, maybe adding some capacitor in parallel, and also how to improve the efficiency, maybe replacing those chips with some capacitive dropper. But of course I will put it in another video, so it's not too long.